The overall power of the J-20 can be described in far greater depth by expanding every dimension of its design philosophy, development path, operational use, and the way its systems interact in real combat conditions. A modern stealth fighter is not defined by one or two standout features, it is the result of hundreds of engineering decisions, compromises, and refinements that all contribute to performance in different phases of flight and battle. A very extended explanation requires looking at how the aircraft's airframe, materials, avionics, mission systems, propulsion, aerodynamics, and tactical integration all work together to create a coherent combat tool. The core of the J-20's power begins with its stealth shaping. Designing a stealth aircraft is not simply a matter of covering a plane with special coatings. Radar detection is based on the way electromagnetic waves bounce off surfaces, and anything that sends those waves back to the radar makes the object visible. Engineers reduce detection by aligning surfaces so the reflections are directed away from the radar source. On the J-20, almost every line on the fuselage is angled with purpose. The forward fuselage is shaped so that its edges, canopy frames, and chines all form a continuous series of planes. These planes direct radar energy away rather than returning it to the emitter. The body transitions into the wings in a blended manner, minimizing discontinuities. The intakes, normally a major source of radar reflection, are designed to hide the engine fan face, which is otherwise a metallic spinning disc that would be extremely easy to detect. The diverterless intakes do this by shaping airflow along the surface, eliminating the need for external intake ramps that usually create sharp, reflective edges. The internal structure also contributes to stealth. The engine ducts curve in a way that prevents a straight line from a radar through the intake to the engine blades. The surfaces inside the ducts are coated with materials that absorb energy. Even small bumps, fasteners, and surface imperfections are minimized or shaped to avoid increasing the radar cross-section. Control surfaces, such as the canards and tail planes, are shaped to function without creating strong radar returns from frontal angles. Even if canards may theoretically increase radar reflection from some positions, the overall shaping and alignment reduce this effect at the most critical angles, and software assists in keeping control surfaces positioned in ways that reduce detectability during important flight phases. Stealth is not only about shape but also about materials. Composite structures are used extensively to avoid the metallic reflections typical of metal skins. The radar-absorbent coatings and layers beneath the surface convert radar energy into heat instead of reflecting it back. These materials must withstand aerodynamic stress, temperature variations, and surface erosion at high speeds. Maintaining the coatings requires meticulous upkeep, but modern designs allow the coatings to be more durable than earlier generations of stealth aircraft. This maintenance capability affects real-world performance since a stealth aircraft that loses its signature control in operational conditions would be compromised. Beyond the physical structure, the J-20 relies heavily on its sensor systems. The main radar uses electronically scanned arrays to steer beams almost instantly across the sky, track multiple targets simultaneously, and adapt its waveform to reduce detectability while still gathering information. The radar's large surface area gives it high power and resolution, which is essential for long-range targeting. But equally important are the passive sensors that do not emit any signals. Infrared, search and track sensors detect heat signatures from aircraft engines, wings warmed by friction, or even the wake created by turbulence. These passive systems allow the J-20 to track targets without revealing its own position. They are extremely useful against stealth aircraft that may evade radar but still generate heat. The jet's electronic support measures detect radar emissions from other aircraft or ground stations. By analyzing the characteristics of those emissions, such as frequency, pulse shape, and timing, the aircraft can identify the type of radar, estimate the distance, and even figure out whether it is being targeted. This information feeds into the aircraft's computational systems, which fuse all the sensor inputs into one continuous battlefield map. Sensor fusion is a defining feature of fifth-generation fighters. Instead of the pilot looking separately at radar screens, infrared screens, electronic warfare warnings, and navigation displays, the system creates a single simplified visualization that highlights threats, targets, friendly aircraft, and terrain. This allows the pilot to make faster decisions and reduces the cognitive load in high-pressure situations. Long-range missiles form the offensive core of the aircraft. The J-20 is built around engagements well beyond visual range. Its internal bay carries multiple long-range missiles, each capable of guiding themselves in the final phase of flight while relying on mid-course updates from the launching aircraft or other supporting platforms. These missiles can be launched before the enemy is aware of the launch platform's exact position. The J-20 can fire a missile, turn away, and leave the missile seeker to finish the job. This style of combat reduces risk to the launching aircraft and leverages the stealth advantage. The ability to use long-range weapons effectively depends on accurate tracking, secure data links, and the power to stay hidden long enough for the missile to approach its target. Engines play a significant role in determining how the aircraft performs in real combat. Improved engines give the aircraft better acceleration, which is crucial during interception missions, better climb rate, allowing it to reach altitude quickly, and better high-speed maneuvering, allowing it to change direction without bleeding too much energy. Sustained supersonic flight without afterburners is especially valuable because afterburners generate large heat signatures that can be detected by infrared sensors. If the aircraft can cruise at high speeds without afterburners, it maintains both performance and stealth. The engine's thermal management also influences how detectable the aircraft is to infrared sensors. Materials and cooling pathways inside the engine can reduce hot spots, lowering the jet's visible heat footprint at long ranges. The flight control system integrates aerodynamic surfaces, engine thrust, and computer logic to maintain stability. The J-20's canard delta configuration might appear to conflict with stealth principles because canards move and could expose flat surfaces to radar. However, modern flight control systems are capable of micro-adjusting the control surfaces continuously to maintain the best aerodynamic performance while still keeping radar reflectivity minimized. Pilots depend heavily on this software to handle the aircraft at high angles of attack or during extreme maneuvers. The software effectively shapes the aircraft's radar signature during flight, not just the physical surface. Operational deployment further strengthens the aircraft. A single stealth fighter is potent, but a coordinated group supported by early warning aircraft, electronic warfare assets, and ground control becomes significantly more capable. The J-20 is meant to operate within a network, receiving targeting data from distant sensors while keeping its own radar silent. When multiple J-20s move in coordinated patterns, they can create overlapping detection zones while individually remaining difficult to detect. The aircraft can also rely on ground-based radars or airborne early warning platforms to track targets, letting the J-20 remain passive until the moment of attack. Large-scale production effect strategy. Having many stealth fighters allows continuous patrols in multiple regions. It provides redundancy, ensuring that if some aircraft are unavailable for maintenance, enough remain ready for deployment. It also allows for complex multi-aircraft tactics that rely on having sufficient numbers to surround, split, or confuse enemy formations. Training programs improve as more pilots and maintenance crews gain experience, and tactics evolve faster with more operational data. The J-20's ability to switch between a strict stealth configuration and a heavily armed configuration enhances its versatility. When stealth is needed, external weapons are removed. When raw firepower is needed, external pylons can be used. This flexibility allows the aircraft to support missions ranging from air superiority to extended range patrol to escort missions and even to long-range strikes when carrying air-to-ground munitions. All these factors, stealth shaping, material engineering, radar absorption, passive and active sensors, electronic warfare capabilities, long-range missile integration, high-performance engines, aerodynamic stability, advanced flight control software, coordinated operational doctrine, large-scale production, and flexible payload configurations combine into a system optimized for modern air combat. The J-20's strength lies in the way these elements interact, creating a fighter that gains information early, remains hard to detect, controls engagement distance, and integrates seamlessly into larger operational networks. The result is a platform designed to dominate long-range, information-driven aerial environments where detection, reaction time, and engagement range are the deciding factors.